So, back to that, we're going to walk through, now, it's probably going to take a little bit of time, just because I want to talk about every single step kind of in detail so you know what you're doing and why you're doing it. But we're going through a handful of these today, maybe just two, I think that's all we got through last period. But show you all the algebra that you need to check on every one of these rational functions. Now, what happens is that sometimes it's easy work, okay? Sometimes it's maybe not so easy. But if you create a systematic technique for checking everything that needs to be checked on these rational functions, you should be okay. Because you all have the capabilities of doing every single process by itself. But if we have to do 6, 7, 8 processes together for the entire function, you might miss one. Okay? So if you set up a kind of a structure to every one of these problems, it's going to be definitely a lot easier for you. Okay? So the first thing, obviously, as you're factoring that, I'm going to kind of write down here the things you always want to do. And this is the way I do it. This is the order that I do it. I'm not saying it's right, but it does work. Okay?
What was the last one? Extra festivals.
All right, so as you factor that, and I'll go up to the whiteboard and show you the factoring for the numerator. You've got multiple techniques you could use. Quadratic formula, you can do all that kind of stuff. I think that maybe is a little bit more time consuming. That one, remember, as you work through factoring, you kind of have a hierarchy of strategies. Okay, first thing you want to do is see is there a greatest common factor? Can I take a 2 out of everything? Okay, if not, go to the next thing, which would be factor by grouping. That's the A-C method, A times C. If that doesn't work, you do have the quadratic formula. Okay, if that doesn't work, you do have your P over Q, your rational root theorem stuff. So I would, and sometimes maybe I don't have a GCF, but this thing will factor using the product times sum method, kind of algebra 1 factoring. But kind of use a hierarchy like that. I would not jump straight to quadratic formula because it's going to be a little bit more time consuming. I would not jump straight to this. They will work, but more time consuming. Okay. This one here is going to actually factor by A times C. I want to check that. And you can do that quickly. Okay. 2 times -4 gives me -8, right? -8, and I think about the factors of -8. There's not too many of them. Do any of them add up to 7? Okay, so they do. So I've had -8, so doesn't -1 and 8 add up to 7? Okay, so I'm going to rewrite this thing as 2x squared Now it doesn't matter the order, minus 1 or plus 8. So I'm going to put plus 8x, minus 1x, then minus 4, right? That still ends up being 2x squared plus 7x minus 4. The reason we did that is so we could factor by grouping. Okay. 2x comes out of the front, gives me x plus 4. A negative 1 comes out of the back, leaves me again x plus 4. So there's where you see the 2x minus 1 and the x plus 4 as my factors. You could have done it as 2x squared minus 1x plus 8x minus 4. Group those first two, group those last two. Now only an x comes out of the front, leaves me 2x minus 1. A 4 comes out of the back, leaving me 2x minus 1. And again, the same exact factors, right? Okay. My suggestion to you, I told the last class this as well, do the factoring by hand, but then, if you want to go to GeoGebra, I think I've shown you guys this before. You can type in a GeoGebra, you can just type in the word factor, and then type in the expression that you want to factor, and it will factor for you, okay? And that's if you go to View, go to CAS, okay? Then that window should pop up, and you can type in right there, okay? Use that to check yourself, because what ends up being problematic with this stuff, if I factor that wrong, all this stuff afterwards is going to be wrong, right? So as you start going through these problems, and just in general, as you start going through these procedures throughout this course, throughout trigonometry, throughout calculus, through physics, they become very kind of step-oriented, right? You have a lot of things to do. I would not check at the end. I would check periodically throughout. I do a factoring, check it, okay? Do a maybe a system of equations that we'll see here in a little bit, and I would check that real quick, okay? Just to keep going through every time I do some new procedure, check it to make sure that it's not wrong, because if I'm going to use that later and it's wrong, it's going to make that later thing wrong, right? Okay, so don't just wait to the end to check your answers, okay? What you want to do every single time that you factor these things, the first thing you want to do is to check to see if there's any common factors, okay? So I look at the x plus 4 in the numerator, and we'll compare it to everything in the denominator. And there's nothing that has x plus 4 down there, right? Then I go to the 2x minus 1, and I compare that to everything in the denominator. And there's no 2x minus 1, okay? We'll see an example here in a little bit that there is a common factor, and see what that tells us, okay? But that's the first thing you want to do. Not every single rational function is going to have a common factor. So what happens is you might do 5, 6, 7 of these things that don't have a common factor, and then the 8th one has a common factor. And you've gotten in the habit of not needing a common factor, not needing to look at them, and then on the 8th one you need to, and you forget to. Does that make sense? Okay? So make sure that you kind of construct a system that forces you to look at these things, even though maybe a lot of times the examples don't have it. Okay? So check common factors, don't exist. Next thing we do is find vertical asymptotes. Okay? And it doesn't matter how you find the rest of these things. These two are dependent on one another, so they have to kind of come in that order. But everything else is kind of, as you want to do it. Okay? But my suggestion is don't flip-flop between, I find vertical asymptotes at first, and then on the next question I'm going to find x-intercepts first, and then on the next question I'm going to find y-intercept first. Develop a system that you are comfortable with, you're able to remember, and you do it every single time. Because then you're not going to get to a problem where you forgot to find x-intercepts. You're not going to get to a problem where you forgot to see if you cross the horizontal asymptote. Does that make sense? Okay. But these are, once I find horizontal asymptote, the checking of crossing that is the only thing that's the only thing that is dependent in this list. So they can flip-flop and do them in any order. I like to do vertical asymptotes. I think that's the easiest thing to come up with. Remember, that's when your denominator is equal to what? 0. Okay. Vertical asymptotes, remember, those are graphically the domain issues for your rational functions, where you divide by 0. So I'm going to set the denominator is equal to 0. So x minus 1, x plus 2 equals 0. And that's going to provide two vertical asymptotes, one at x equals 1, and one at x equals negative 2. Those are my vertical asymptotes. Once you've done the factoring, guys, most of the work is already finished. Okay, you just have to take x minus 1 and realize, well, that's x equals 1 for an asymptote. You take x plus 2 and say, well, that equals x, or that is x equals negative 2 for an asymptote. Okay, the biggest and most challenging amount of math or amount of arithmetic happens when you factor. Everything else is kind of understanding of how your values of x are impacting your function. Okay? The next thing we're going to do is find a horizontal asymptote. Okay? Remember, a horizontal asymptote is kind of a three-part process, or you got three options, and it's all dependent on the leading degrees. Okay? So we're going to compare leading degrees. Okay? I'm just going to write this as a x to the m over b x to the n. Okay, so we had three parts yesterday. It said if m equals n, then you have a horizontal asymptote at y equals a divided by b. If these two exponents are the same, you simply divide your coefficients up front. Okay? If m is less than n, okay, so the denominator is a bigger power, then your asymptote is at y equals 0. Okay? Those are the two options that I want to focus on right now. Tomorrow, or maybe even the next day, we'll get into the third option when the numerator is actually bigger than the denominator, and that creates slant asymptotes. Okay? But that's what you want to think about every single time you find a horizontal asymptote, or you're trying to find horizontal asymptotes. Okay? So for us, if we look at our original polynomial, our original rational function, I guess, these two polynomials, okay? I think it's best to look at it in expanded form. It's easiest to look in expanded form because it's obvious what our leading terms are, right? Leading term is 2x squared here and x squared on the bottom here, right? You can't recognize that very easily over here in the factored form. So even though we want to always factor these things initially, we still want to have both formats, the expanded format and the factored format, in front of us because we're going to gain information from both of them. Okay? So my leading degrees in both of these are x squared, right? There's my 2x squared and my 1x squared. Okay? So that's this situation where the numerator's exponent is exactly the same as the denominator's exponent, so then all we have to do is compare the coefficients, right? And then the logic of this is, think about taking a very, very large number. Take 1 billion, okay? Square it. Okay, 1 billion has how many zeros behind it? So 1, how many zeros? 9, okay? If I square it, I have a 1 with 18 zeros. I don't even know what that number would be, but it's a big number, okay? Multiply that by 2, so now you have a 2, and then a comma, and 18 zeros, right? Okay? Well, then add to that 7 times 1 billion. 1 billion is a huge number, right? Okay? But if I have 2, comma, 18 zeros, then 1 billion is marginal to that value. Does that make sense? Okay? It's not very much. Okay? It's the idea of, you know, maybe we're more comfortable thinking about billionaires compared to millionaires. Both of them set for life, right? But a billionaire has so much more money than a millionaire. You take $1 million from a billionaire, they don't care. Well, they care, but just because of the act, but it's not impacting their budget, all right? So 7x minus 4 and x minus 2, those things are negligible when x is really, really big, okay? So they don't impact what's happening in the long run. We're only worried about the front coefficients, Okay. So what you would have there is up top, if x was a billion, you'd have 2 and then 18 zeros. On the bottom, you have a 1 and 18 zeros, right? Well, what are those 18 zeros going to do on top and bottom? Cancel out. Leave you with what? 2. Okay. So the horizontal asymptote, that's the logic behind finding it, and that's the logic behind why this rule works, is because these values are very negligible in the long run. Okay. So we have a horizontal asymptote. It's an equation. Okay. It's y equals 2 in this case. Okay. So y equals 2 or 1, or just 2. All right. The next thing we're going to do, and this is, I think, actually, this is the hardest part of this entire process, because of some of the results that we get. We have to understand what they're meaning for us. Okay. It says check crossing of horizontal asymptote. Okay. Talked about it yesterday. Is if we want to figure out where 2 lines intersect, think back to algebra 1. And if we had something like y equals 2x plus 3 and something like y equals 10, if I wanted to see where those things cross, aren't these 2 values the same? So what's that tell me about 2x plus 3 and 10? They're the same, right? And if I solve that equation, I find the x value for where they cross. Well, it's the same thing here. Okay? I have an equation, y equals 2. And I have an equation, r of x, but r of x is just a y value. We just use r of x to tell us it's a function. Okay? But we got a y value there. Y equals 2x squared plus 7x minus 4 over x squared plus x minus 2, right? Okay? Well, is that y value, is that y value there the same as that y value there? Yep. So what's that telling me about the 2 right there compared to this stuff? If we cross it, they should be what? Equal. They should be equal. So let's go ahead and go through the math, setting those 2 things equal, and see if we come up with a conclusion that tells us yes, we do cross it, or no, we don't cross it. So I'm going to set 2 equal to. Now, I always like to go back to the original function. Okay? And you're going to see why I like to go back to the original function. I guess I don't want to say original because the way they might present to you. I want to go to the expanded format here. Okay? So what we have on the upper left there. You've seen in your homework sometimes they give it to you in this format, right? Okay? And they've done a lot of the work for you, but there is still information to be gained from the expanded version. So even if they give it to you factored, you probably want to FOIL it out and see what the expanded version looks like, right? Especially in the event of wanting to check a horizontal asymptote. I like to use the expanded version. I'll explain to you why here in a minute. I'm going to take 2 equals 2x squared plus 7x minus 4 all over x squared plus x minus 2. Okay? What happens if I would have used the FOILed, or not for the factored version? I'm going to have to, as I start solving for x, I'm going to have to FOIL it. Does that make sense? So this is already FOILed. Okay, so I allow myself to alleviate a step by using this format. Okay? Now here's the thing. I'm a person and I see that that's a rational equation. You got ratios, and it's an equation, so it's a rational equation. I like to multiply by the least common denominator. Okay? And if you look at this, the least common denominator is x squared plus x minus 2, right? I multiply both sides by that. Okay, so I multiply over here, cancel, cancel, come over here, and then I got to distribute that 2 to it, right? So I'm going to do that, but then I'll come back and talk about maybe an alternative way you could kind of view this. Take that 2 and distribute, so I get 2x squared plus 2x minus 4 is then equal to, on the right hand side, all that's left is the numerator, right? And that's the equation you get when you multiply by that least common denominator. Now, some of you might say, well, you got a ratio on the left, and you got a ratio on the right, correct? 2/1's a ratio. This blue stuff's a ratio. What is it called? We'll talk about this in geometry quite a bit, but what is it called when you have an equation that says two ratios are equal? Starts with a P. Proportion. And how do you solve proportions? Cross multiply. If I cross multiply 1 times that, I get that side. Cross multiply this times that, I get this side, right? Okay. And that's fine. That works every time when we do these throughout this entire section. But my fear is that you get in that habit, and then at some point, maybe you have something like this: 2x squared plus 7x minus 4. I don't know what situation you would be in doing this, but if I have like plus x, and over here I have like 2/1, I get a lot of people who want to cross multiply this. Can I? No. Because to cross multiply, you need one ratio equal to one ratio, right? You have one ratio equal to a sum of two ratios. And that's a problem. That's not a proportion anymore. Where if I wanted to solve this, the best thing to do, I think, would be multiply by at least common denominator. Or, combine these two things, which the way you combine those two things is multiply by at least common denominator, right? So if I do that, every time I see a rational equation, I don't use the proportion technique, because I think multiplying by at least common denominator just kind of kills two birds with one stone, and I don't have to remember two different rules or two different procedures using that. But now what's really nice is that you get a pretty simple equation here. Now it looks problematic, but what's going to happen with the 2x squares? Cancel out. And a lot of times that's going to happen. Okay. What happens with the negative 4s? Cancel out, right? Okay. Now we get 2x is equal to 7x, right? Now I want, because we can go a little bit further, and if we go a little bit further, it makes a whole lot more sense. But is there any value of x that you could plug in there, and you take 2 times it, and it gives you exactly the same thing? If you take 7 times it? 0. Okay? That's kind of, I think, because every other number doesn't work, right? Take 1 for x, you get 2 equals 7. That's a false statement. Take 2 for x, you get 4 equals 14. That's a false statement. And start choosing other values of x, you will always get a false statement, right? So there's an infinite number of situations where that's false. But there's one where it is true, and it's 0. Okay? And some people kind of overlook that. Another way of doing it is just, continue working with this thing. Move all your x's to one side, so I get 0 is equal to 5x. And now it might make a little bit more sense what x value can I plug in there to get 0, right? Okay. So what that tells me, because there is a solution to that, x does equal 0. Okay, x equals 0, I'll write it up here, is where I cross my horizontal asymptote. Okay, at x equals 0, I cross the horizontal asymptote. Okay, we can eventually then plug that back in and find the y value, but I think there's some work here in a moment that's going to get that for us anyways. Does that make sense? So you do cross it. And remember, I told you, you're going to cross horizontal asymptotes relatively close to 0, 0, right? Is that relatively close to 0, 0? Yeah. Okay. Now, as you go through, that's not always going to be the case. You might get down to an equation where you're left with like maybe everything cancels out. Let's see. Just got to give you an example here. Let's go like 2x squared plus 5x minus 3, and then up top, or on the other side, you would have like 2x squared plus 5x minus 7. What's going to happen to my 2x squares? Cancel. What's going to happen to your 5x's? Cancel. And you're going to be left with negative 3 equals negative 7. Okay? That's a false statement, right? And when you get a false statement, it tells you no crossing. Does that make sense? Okay? So false statements, you will never. That tells you that you do not cross that horizontal asymptote. The statement we have on the smartboard, the 0 equals 5x, that is a true statement when x is 0, right? Okay. But negative 3 equals negative 7, that will never give me ever a true statement. That's false all the time. Okay. So that's kind of the difference between the algebra there, when you will cross it and when you will not cross it. Okay. That doable?
Yes.
All right. Like I said, I think that's the hardest part of these problems. Is using that. You know, it's an algebra 1 concept, but using that to check for crossing of a horizontal asymptote. And I really think the hardest part is when you see like -3 equals -7, and remembering what that means to us. Okay. All right. So the next thing we'll do is find x-intercepts. Okay. Well, finding x-intercepts. Basically, all you're going to do is you're going to take this function, and if I want to find an x-intercept, what coordinate is 0? Come on. The y, okay? So y is 0. So y is my r of x, right? So I'll make that 0. Now the idea here is that this is the exact same algebra that we just did to see if we cross the horizontal asymptote. Okay? We're crossing the horizontal asymptote. The quantity over there was 2 instead of 0. Okay? But we can still use maybe if you want to use proportion ideas, use your proportion ideas. If I cross multiply, what's 0 times that denominator going to give me? 0. And then you're left with 0 is equal to just x plus 4 and 2x minus 1, right? Think about this in general. Will I ever, if I'm looking for x-intercepts, is this number ever going to be anything other than 0? No, that's the definition of an x-intercept, right? That has to be a 0. So will I ever cross multiply? No matter what is down here, when I cross multiply, will I ever get, and if you guys remember, those are the means, right? Or sorry, no, those are the extremes. The middle ones are the means. Will I ever multiply my extremes and get something other than 0? No? You guys remember the phrase from geometry, the product of the means is equal to the product of the extremes? Okay? So if I multiply those things, I'm always going to get 0, no matter what is down here. So that is kind of a shortcut that if you see, you know, my list of rules on the website that says to find x-intercepts, you set numerator equal to 0. Okay? Because every time when you cross multiply, your extremes will give you a product of 0. Okay? Your means will give you just your numerator. Okay? Is that doable for everyone? So that's kind of easy. Then once you understand that concept, is it pretty easy to find my x-intercepts? -4 and what, 1/2? Okay. Now your y-intercepts, and you can look at y-intercepts in either one of these things, but y-intercepts is when x is what? X is equal to 0, and then I evaluate. Well, if x is, I like to look at the expanded version because I think it's easier. If x is 0, what happens to this term here? Cancel that, goes to 0, right? What happens to this term? Yeah, 0, 0, 0, right? And what you're left with is -4 divided by -2. What's that give me? 2, right? Okay. So my y-intercept is 0, 2. I like to look in the expanded version to find that. But if you were to find, you can find it up here. Okay, if I'm looking in that FOIL version, I just simply plug in 0. I get 4 there. Plug in 0 here, I get -1. Plug in 0 here, I get -1. Plug in 0 here, I get 2. Multiply those through, I get -4 over -2, which is that still give me 2? I think that's more work. Even though that's not a lot of work, I think it's more work than maybe what's necessary if we look at the expanded version. Is that all right? All right. So if we do all that stuff, you've got everything you need to do these last two things. Okay. We're going to graph it, and in the event of graphing it, you might need some extra test points. Okay. So I've graphed this, or I guess I've already graphed the asymptotes here for us. I think it's a good idea as you're going through this stuff to label. So this is an asymptote of x equals 1. This is an asymptote of x equals -2. this is an asymptote of y equals 2. We had a x-intercept of 0, -4. I'm sorry, -5. -4 is 0. And I'm going to put that actually down here. -4 is 0. We had a y-intercept of 0, 2. And we had another x-intercept of 1/2, 0. With that information, so that's all the information that we just developed through our algebra. We have a good start to graphing this thing, okay? And as you graph this, if you were to look through the PowerPoint goes through, and your textbook does the same thing, and walks you through some kind of iterative processes that you just choose values and plug into your function and see whether you get positive y values or negative y values back, and you plot those points, and it's a lot more work than what's necessary. All right, so I'm going to kind of show you a way to do this, but you have to have some thought. You have to be intelligent about the points that you have and what they're telling you. Okay, this point here tells me that that is an x-intercept, and I don't have any more x-intercepts in. Let's see here. Our asymptotes kind of block off regions, right, of our two-dimensional plane. Because I have that one x-intercept at -4 is 0, what that tells me in that region is I have no more x-intercepts in that region. Okay? So my graph is kind of forced to do something particular. Okay? It doesn't have a whole lot of options. For instance, my graph cannot come up here and then come back down, right? Because if it came back down, the algebra would told me there would be another x-intercept, correct? Okay? Some other things that cannot happen. Let's say that as I move to the right, can my graph go that way? What did I just cross? Horizontal asymptote, right? Okay. And our math has shown us that we only cross the horizontal asymptote right there. We can't pass that vertical asymptote, right? So there's no way to go up and then come back down and cross through that one there, because we're not allowed to cross that vertical asymptote. So my graph can't do that. My graph is pretty much restricted to being able to do that and that. Okay? As I move closer to a vertical asymptote, my graph kind of sucks either to negative infinity or positive infinity. In this case, it's going to get sucked, my y value is going to get sucked down to negative infinity. And as I move to the left here, my y values get sucked up to whatever that asymptote is at. So that asymptote's at 2, my y values are approaching 2. So that's what kind of that curve looks like in that region. Does that make sense? Okay. Someone last class said, well, why can't I do this? Why can't, I understand I have to go down this way, but why can't my graph maybe do that? Because sometimes you will see a graph kind of give a little bump and then go back down. But why can't I do that? Wasn't it said that I had to have another x-intercept there? Okay. So we can't do that. So I think that's once you get a hang of that and understand that the information you found algebraically, there are no other things in here. There are no other x-intercepts in here. Okay, you've already done all the work to tell you exactly what you need to know. If we can logically piece that stuff together, it's going to be a lot less time-consuming, I think, finding your graph for this thing. Okay, I'm now going to look at these 2 points because they're in between. Let's kind of look at my highlighter back here. Let's look at that asymptote and that asymptote, and look between them. Okay. I guess before we do that, we should probably state that if I've got my graph here in the bottom, then it can't exist up here on top of this asymptote, right? Because we know that we don't cross this at horizontal asymptote anymore. Okay, in this blue region. So if the graph is existing down here, then there's no way it can exist up here. So you go to the next region. Now in this next region, and this is usually where you're going to cross your horizontal asymptote. We're going to look at the region between those two vertical asymptotes. And we see here that at this point here, my graph, I'm going to have to move left and right from that point, right, to get my comprehensive graph. So let's move to the left first. If I start moving and tracing to the left, think about the options that you have. Okay? I could go down, right? But if I go down, I've got two options. My graph could continue to go down, right? But hopefully you realize that that can't happen. Why can that not happen? There's no other x-intercept over here, right? We haven't found that. Okay? My other option is maybe to, you're saying, well, what if it goes down and then comes back up? Can I do that? Why not? Yeah, because now we're seeing that across the horizontal asymptote a second time. In our algebra did not show that. Okay? So our only option here, if I can't go down, then my graph has to go up. And then it gets sucked to that, as you get closer and closer to a vertical asymptote, it gets sucked up to infinity, or negative infinity in this case, up to positive infinity. Does that kind of make sense? Now from that point, I've gone to the left. Let's see what our graph should look like as we move to the right. Okay? Well, you got two options again. I could either go into the right, get sucked up there, right? Okay? But what's that point telling me? Yeah, I got to cross that point. So maybe it does go up, but it'd have to come back down, right? If it was going to have to go up and come back down, would it cross the asymptote again? And I'd have that algebra to show that, right? I don't have that algebra. So my only option is to go from that y-intercept down through that point. And now once you get to that point, I got options. Can I continue to go down and then maybe bounce back up, or just continue to go down, right? Which one do I do? Just continue to go down. Why don't I bounce back up? Yeah, if I was going to bounce back up, I'm going to need another x-intercept, right? And I don't. Okay. So providing x-intercepts, y-intercepts, that's why we do that. They're the, I say additional test points. Okay, extra test points. These are basically test points for all these regions, but they're really good ones because they're easy to find. Because once we factored, we have all the work done to provide those points pretty easily, right? Okay. Now we don't know what's happening over to the right-hand side. Come on. So we don't know what's happening over on the right-hand side of that asymptote at x equals 1, right? Okay. So here's where we need to test points. Okay. And it doesn't matter what you choose. Choose an x value that is over here. Okay. So I'm going to choose an x value. That's 1. So let's just choose 2, right? Don't choose anything ridiculous. Don't choose like 1.5 or 3 halves or 15 thirds or something like that. Well, that'd be easy. But 15 fourths. Don't choose something stupid. Okay. Choose an integer, because what we're going to do is we're going to come back up to our original function, okay, and we're going to use a test point. Now, you can plug into either one, but I think this one's probably better to plug into. Okay, I'm choosing x value of 2, right? If I plug in x value of 2, what do I get right here? 6. And what do I get right there? 3. So my top becomes 18, right? If I choose 2, what do I get here? 1, and what do I get here? 4. So my bottom becomes 4, and that's 9 halves, right? Or 4.5. So an x value of 2 provided me a y value of 4.5. So 4.5 is about right there. Okay? So there's a test point. Okay? But that test point tells me a lot. It tells me that the other points that are close to it should be in the same region, right? And it also tells me that as I move to the left from that point, I've got two options. I can go up or I can go down, right? But if I'm going to go down, my algebra that we've already done should tell me that I'm probably going to have another what? Another crossing of the horizontal asymptote and probably another x-intercept, right? But we didn't have that stuff. So I'm probably safe to say that we're going to go up. Okay? Now, as I move to the right of that point, okay, we should get kind of sucked down to that asymptote, right? That horizontal asymptote. Do I ever cross it? Nope. there's my asymptote, graph looks something like that. You know you don't cross this because your algebra told you only cross it at 0, 2. And if I can't cross it anywhere beyond over here, that means that if my curve is existing up in this region here, there's no way that it can exist down here. And I'm done. That's the comprehensive graph. Okay. You can test this in GeoGebra. Okay. I went ahead and last period just typed this in. I think and I put in the asymptotes as well. Okay, so if I graph it initially, that's what it looks like. But putting the asymptotes kind of mimics my graph a little bit better, I think. Okay, so you can double check that kind of stuff with GeoGebra. You can also do the same thing with TIA 384. And now I know this doesn't happen on everybody's, but it does happen on some people's, so I'm going to talk about it. All right, so I typed in, the only thing I'd be careful with when you type these in, rational functions into your calculator, you need to make sure that your numerator has parentheses around it and your denominator has parentheses around it. If you don't, okay, if I left all parentheses out, my calculator is going to do all the multiplication first, okay, but eventually, so I guess it'll do this multiplication first, it'll do this multiplication second, and then it'll do -4 divided by x squared. And we didn't have anywhere in this problem -4 divided by x squared, right? So we got to make sure we put parentheses in there on the order of operations. You don't mess up and the graph's going to look completely different than what we want. So I type that in. You type it in factored form or expanded form, and then I graph it. Okay. Now some of yours, when you graph it, and I know because people have came to me already and talked about this, some of your graphs will have those lines in them. Okay. And what do those lines look like for us? They look like the asymptotes, right? Okay. You can treat them as the asymptotes, but they're not really asymptotes. What your calculator is doing is that if you go to mode here, maybe, you go down here, see where it says connected? Okay. What the programming of your calculator is doing is saying, in the background, we're finding all these ordered pairs, all these coordinates, okay? And it's saying once I find successive coordinates, that connected tool says find that point. Because we're in the connected mode, use a smooth curve to connect them. So it really doesn't maybe find all those points on the inside. It just finds some critical ones and connects them with smooth curves. Does that make sense? So what it's doing then is eventually it's finding some point down here, some y value, maybe the last y value on the left-hand side of that asymptote that it finds. It plots it. And then it jumps over that asymptote, knowing that you can't divide by 0, so it jumps to the next value beyond that, and it plots some point all the way. That's frustrating. All right, so it plotted some y value all the way down here, and then it jumps up here and plots a y value all the way up there, and it says those are consecutive y values, right? Consecutive points, so connect them, all right? And because they're so large in the y values of being negative y and a very large y value up here, that line connecting, that curve connecting looks linear. And it looks like it's purposely putting in the asymptote. It's not. It's trying to connect a point down here and a point up there. Does that kind of make sense? All right, so I wanted you to understand what it's doing and why some people show them and why some people don't. Some people don't show them. Mine doesn't show it because I have a newer operating system, newer programming in which they fixed that, right? If you're a person that doesn't want that to show up, you don't want those things to be there, those asymptotes to, or what looks like to be asymptotes, you can go down here to the connected mode and go to dot, hit dot. Now there are applications for dot, but I don't like it because it's kind of crappy. And that's kind of what your calculator would be doing in connected mode, is finding those points, okay, and then connecting them with a smooth curve. Does that make sense to everybody? There is some other stuff. What time we get out here? 58? 56. You're going to see a question in your homework, and it happens not very, I don't want to say very often, but it's infrequent, I guess. If I have r of x is equal, and we'll talk about this in more detail tomorrow, but I want to make sure that if you start working your homework tonight, that you can do this. Let's say I start with a function like that, okay? Top's already factored, the bottom could be factored a little bit more. I get x minus 3, x minus 3, right? That's the factored form. This is what I was talking about earlier, is that doesn't always happen, but occasionally it does happen. Do we have common factors here? They can cancel out. Common factors give me a 1, right? X minus 3 divided by x minus 3 is just 1. So we cancel those out. When we cancel those out, what we're left with is 1 over x, right? Okay? But that x minus 3 is important to us because x could not be 0, right? Or sorry, not x. X cannot be 0, but it cannot be 3 either. If I plug 3 into this original function, do I get 0 on the bottom? Okay. So even though it canceled out and I'm left with this, my final graph is going to look something like that. That's 1 over x. That's what that looks like. Okay. But the point where x is 3 does not exist on that graph. Okay. So this is the algebra we go through. If I have terms that cancel out like this, factors that cancel out, that factor, x minus 3, provides me with what we call a whole, okay? So common factor provides a whole, not really a math term, point discontinuity is the math term. Okay. So I take the x minus 3, set it equals 0, x equals 3. So we have a whole or point discontinuity at x equals 3. Okay. So I go out to my graph, 1, 2, 3, and I go find the point on my curve, and I put an open dot there. Does that make sense? And now that's my point discontinuity. Tomorrow we'll talk about how to find that y value. Finding that y value is really easy. All we have to do is plug it back into this simplified version of your R that's going to get 1/3. So we'll talk about that again tomorrow. Keep working on that assignment. The assignment's not going to be due tomorrow. I probably won't change it for a while, but